quick introduction from myself. My name is Niels Oosthuizen. I'm an electrical engineer at Jubaili Bros here in South Africa. I will be presenting today's topic for you on string sizing and proper PV design. I have enabled my pointer, so at times I will be indicating to a specific point on the presentation, just as a point of clarity. If at any stage we have experiencing problems in audio or video, I'm trying to keep a lookout on the chat, so just let me know if there's any problem that's going to come up. Right, quick one. We're just going to run through the timeline about Jubaili Bros, when the company was established and how the company has evolved. Quick points of reference is the company was established in Lebanon in 1977. On this timeline down here below, you can see how the company has progressed or as they opened new branches. UAE branch was in 1992, Nigeria in 1996. Specific to myself, South African branch was established in 2016. And then in 2017, marking the 40 years anniversary of Jubaili Bros, the solar division specifically was established. And that was just the company and the family realized that the company needs to evolve with technology and with modern day. So they've established a renewable energy division or a solar division. Since 2017, we've opened branches in Pakistan, Kenya, and there's still some expansion being planned for 2022 and beyond. Also, a nice point of reference is that Jubaili is also expanding its product offering to be a complete power solution provider. So if you've got any power solutions that you would like to inquire about, please send us an email and we will gladly assist you. And then also please follow us on LinkedIn, and then you will also see the latest updates there and partnerships that we're forming with other companies as well. In this next slide is just a global map. On this global map, every point where you see a flag, as well as the name of the country, we've got representation in that country. It can either be a physical office, sales office, or in some of the countries we actually have full factories assembling generator plants for us. But in each place where you see a flag, Jubaili has got a sales presence. This next slide is actually a very important slide. It's the 6 pillars of support that Jubaili offers. First of all, if we look at that product supply, it's exactly what the name implies, is that we sell you whatever you require. So if you require CKD components or inverter or whatever it may be, we will supply you that specific component. The next pillar is an expansion to the product supply is training. We can then provide you with training for the product that you purchased. So if it's pre-sales training, where we can assist you on training you on what's the capabilities of the product, but then training can also be after-sales training, where we provide you training on perhaps operation and maintenance of the products that you have purchased. So second one, training is very important to the first one. Then the third one is engineering support. So as Jubaili Bros, we have qualified electrical engineers that's available to assist us. So if you've got any design inquiry that you would like assistance on, please feel free, email us your design, email us your query, and then we will support you in any which way possible. Please note that this engineering support is free of charge to a very certain limit. In South Africa, for specifics, in South Africa, we're not going to have the engineer sign off a drawing for you. You need to have your own engineer signing off designs and drawings, but we will definitely support you on this to optimize your system, to have the best possible system with regards to efficiency and product selection. Moving over to the fourth one is leads. So as Jubaili Bros as a company, we are not here to compete with you. All of you guys that's on this presentation, you are our customers. We would like to remain loyal to you, and we would like to see ourselves as being part of your business. So whenever a big corporation approaches Jubaili directly for a project, we will then refer this project to one of our EPC's clients that we feel will best suit the need of that project. So if there's any leads that's coming straight to us, we will then refer it to you guys. The fifth pillar is referral to finance. So Jubaili Bros itself does not currently offer financing solutions, but we do have partnerships and relationships with banks and financing houses or personal finance. So if you need finance for a project, we all know that solar projects has a big capital expenditure initially just to get the project started off. So if you're in need of finance or you have a project that you need finance of, again, please reach out to us. We will then link you up to the relevant institution that can assist you best. Then the sixth pillar of support that we offer is after-sales support. So our engineers can assist you with site support for commissioning of the solar systems, after-sales maintenance, and timely warranty support. So the after-sales support is something that we pride ourselves on. We do not just sell you something and then leave you out hanging to dry. So if ever you have any issue on site, we will gladly assist you. There are certain channels to follow for the support. We can first try remote support to see if we can solve the issue. If remote support doesn't work, we can always try and schedule a site visit to physically be on site and see what is the best way that we can assist you in solving your problem. So Jubaili Bros has specifically partnered with Huawei. We are a value-added partner for Huawei and a certified solution provider for Huawei, meaning that we can assist you from start to finish on the whole project. If it's a simple residential solution, all the way going up to utility scale. Why did we choose Huawei? Well, Huawei inverters typically produce higher yields. The smart operation and maintenance aspect of the Huawei inverters lowers your operational expenditure. And then Huawei inverters are very safe and reliable with a 25 years reliability. And then what we also like about Huawei is that when it comes to warranty support, if there's a fault in an inverter, it's as easy as replacing it if it's a valid claim. So it's not components being stripped out and then fixed. If there's a problem, the whole inverter gets replaced. Right, moving on, we're now actually going to start with the actual section on today's topic, the string sizing and proper PV design. The initial section was just an introduction to Jubaili Bros and our partnership with Huawei. So today's presentation is actually split up into 4 different sections. Number 1 being determining system capacity. Number 2, equipment selection. Number 3 is the string design. And number 4 is running a simulation. So on the first section is determining the load requirement. So we start off with the load requirement to determine the desired AC output. So typically you look at electricity bills and make an estimate, and then for more detailed analysis, you can leave a load analyzer for 7 days and view the load profile. So on this graph on the right is a typical load profile. So in blue, you will see the average daily load. So that's the actual consumption of electricity. And then on the red, you've got your solar capacity factor. So solar capacity factor is how your solar will ramp up in the early morning, reach its peak around midday, and then gradually decrease again. So this is the typical solar capacity factor, and it would typically be between hours of 6 to 5, but then your most optimum, or inverters actually producing proper, would be from 8 o'clock to 3 o'clock. So this one is just typical to residential. You can see that the demand is in kilowatt hours, and it doesn't even go above 5. But then this is also the same for commercial installations or commercial sites. And then typically you have two options when deciding on your system capacity. So some of the EPCs or designers prefer to design a system based on the peaks. So if you look at the peaks of the loads, in this instance, it would be 4 point something. So that's one way of designing it. The advantage of using peaks for your design would be that if the load increases in future, you're still covered for a larger section of the demand. Another option in determining the size would be to work on average. So if they were averaging out this daily load graph, where it's between 4.2 and let's say minimum 1, let's say you would work on an average of 2.5 or maybe 3. So then you would design your system on the 3 kilowatt. But then the problem with this, or not really a problem, but what then can happen is that if there's expansion to your load, or if you're on a commercial site, your factory, then your PV system is then typically only for an average. And then if you expand it, then your average would actually be increasing and your PV would only be covering a minimum. But then also, if you're only limited on finance or space available, then you would probably use your average load as a design requirement. So the second thing to consider is space constraints on your system designing. So solar system site area is one of the biggest constraints limiting the solar system capacity. So below you typically have three places where you can do installations. So figure one would be concrete rooftops, or second one would be ground mount, and the third one would be flush rooftops. So each one you would perhaps look at the physical space on top of the roof that's available. If it's, for instance, a flat concrete roof, you always need to double check that your spacing in between rows is of such a distance that the one row doesn't cause shading on the second one. So that's definitely a space constraint. Figure two, ground mount. Ground mount, again, you might have abundant space, but then also please be aware of the spacing between rows so that one row does not cause shading on the other one. Then the third option for mounting would be flush rooftops. So flush rooftop, your constraint on space is the actual roof space available. And then if there's anything on top of the roof, chimneys, turbines, or even billboards next to your building that can cause shading, please take it into account as a constraint. Then moving over to the next one is on determining your system capacity is DC to AC ratio. So if we look at this first picture here, it's got a DC to AC ratio of 1, which means that the PV capacity is equal to the inverter capacity. So in this instance, we're looking at a 300 kilowatt system. So it's 300 kilowatt of inverters, but then also the PV is 300 kilowatt. So if you look at the solar capacity factor, maximum that you can get out of it is 300 kilowatt. But then if you look at the picture on the right, it's got a DC to AC ratio of 1.25, meaning that PV capacity is 1.25 times the inverter capacity. So why do we go for a higher DC to AC ratio? So if we look at the same graph again, our inverter capacity is still 300 kilowatt, but then our PV capacity is 375 kilowatt. So just for reference, if the yellow is greater than the red, it provides efficient return on investment. So the red is the section here where it's greater than the inverter capacity. And the yellow is actually now the new solar capacity factor with the excess PV, or the PV that's greater than the inverter capacity. So the green section would be similar to the initial one where it was a DC to AC ratio of 1. Then with the DC to AC ratio of 1.25, we're actually looking at a solar capacity factor on the yellow segment now. So you would see that on the yellow segment, you've got earlier production in the morning, and you also have later production in the afternoon. But then if you look at your midday or your peak capacity, your peak performance might be higher than your inverter capacity. So this red section is then the lost power due to inverter clipping. But we also need to understand that this only happens at very peak hours of the day during very peak days of the year. And this does not yet factor in cable losses or any other inefficiencies in the system. So this is all looking at, almost want to say, lab conditions or data sheet conditions. Then your graph would be looking like this, but it's not typical in the real world. Then, as I've mentioned, extra power in the mornings and evenings in this yellow section. So that is what's happening every day if your DC to AC ratio is more than 1. Continuing on the DC to AC ratio, the ratio of DC capacity is the quantity and wattage of solar panels to the inverter's AC power, and that is what is called the DC to AC ratio. Generally, we recommend it to be between 1.2 and 1.4. In South Africa, my personal advice would be to have it between 1.15 and 1.3, and that's just because of the abundance of solar irradiance that we've got in the country. So why do we do a greater DC to AC ratio? This is due to system losses and also the fact that peak sunlight is only for a few hours per day. So clipping will be small, but extra production in non-peak hours will be large. So if we refer back to the previous graph now again, that's just referring to the extra production you get in the mornings. And then this clipping is only for a very limited amount of time. So how is the DC to AC ratio calculated? So if you've got a module 450 watt peak, 28 panels, that means that your DC is 12.6 kilowatt, your inverter is 10 kilowatt. So you just take the 12.6 divided by the 10, you get 1.26. So that's how you calculate your DC to AC ratio. Then the next one, it's just another example. Again, we're using 450 watt modules, but we've got 18 modules per string and we've got 16 strings. So then your calculation would be the module wattage times the pieces per string times your number of strings, and then you divide it again by your inverter capacity. That would give you a DC to AC ratio of 1.29. Okay, moving over to the second part of this presentation is equipment selection. So equipment selection on the DC component side, what are you looking? You're looking at your panels, your PV modules, you're looking at the mounting structure. Then on AC components, you're looking at your inverter and accessories. So it's inverters, communication devices, and power meters. So these components is now typical to a grid-tied scenario. If you're looking at a hybrid solution or off-grid solution on your DC side, you will be adding more batteries and battery management systems. But on this system, we're looking at an AC grid-tied. Typically, the Huawei inverters are grid-tied AC inverters. There is battery storage solutions available from Huawei. We've got 200 kTL inverters that's working with 2 megawatt hour battery containers. But then also later this year, Huawei will be releasing a commercial and industrial size of 200 kilowatt hours, working with a 50 kilowatt power control center. Equipment selection, PV panels. So PV panels, your modules. So what do you look for when you're selecting your panels? It's important to look at your maximum power voltage, maximum power current, open circuit voltage, short circuit current. So typically the open circuit voltage and your short circuit current is your limiting factors or your deciding factors when choosing either a module or inverter. Always be wary to do a comparison between your panels and your inverter. If I can just mention it quickly, we recently had a project in South Africa where the EPC was using a module that had very low open circuit voltage of 37.9 volts, but then the short circuit current on those panels were a lot higher. It was 18.52. So in their design, they could not use both inputs on the MPPT. They could only put one string per MPPT because the inverter could only handle 30 amps on the MPPT. But with the 18.52, with two strings that then attached to that one, it would be a lot greater than what the inverter could handle. So they would be running into clipping issues. So on a short circuit side, they might have been fine, but they would have been clipping because the inverter could handle 50 amps as a short circuit, but then on the operating current, it was going to pass the 30 amps. So very important, have a look at your open circuit voltages, your short circuit currents, and then also your temperature coefficient on V open circuit that determines the number of modules that you can use. So on PV panels, please have a look at your data sheets, have a look at your designs and see what's going to be optimum for your selection. Again, this is just continuing on PV panels. PV panels, you've got STC as well as NOCT ratings. STC ratings is almost lab conditions, where it's your standard temperature, but then NOCT ratings is your normal operating sub-temperature ratings. But normally for design, you use STC ratings, although NOCT ratings is closer to reality or what's going to be in practice. Mounting structure, that's your second equipment selection or the third one. So when selecting your mounting structure, you need to look at your installation type. You need to look at your rooftop material and type, arrangement of the solar panels, and orientation of the panels. So on the roof type, there's different variety of rooftops available. Please, if you want us to assist you with the mounting structure, please give us all the details so that we can assist you with using the correct mounting structure. I think using incorrect mounting structure is one of the worst things that you can do for a PV system, as it might cause you hefty losses in future if there's damage to your system or to your rooftop. Inverter selection. So when it comes to inverter selection, there's quite a few options available. You're looking at your AC capacity, you're looking at your output voltage, and you're looking at your input voltages. The input voltages is typically your input voltage from that's going to be from your strings on the DC side. Output voltage, if you're looking at the small commercial industrial inverters, your output voltage is typically 400 volt three phase. But then if you look at higher voltage, not higher, but more medium voltage, like the 200 kTL has got an 800 volt output. So if you're not wary of the output voltage, you might need a transformer station either to step the voltage up or step the voltage down. So that is all determined about where's your tying point on the AC side. Are you tying in at a normal 400 volt, or are you tying in at a distribution level of 3.3 kV, or perhaps transmission level of 11 kV? So from Huawei side, if you look at the small CNI inverters, you've got 12 to 20 kTL. Then small to mid-range is 50 to 40 kTL. Mid-range is 50 to 60, and then the 100 kTL is our most popular one in South Africa, and that's the one that's being sold most. Then moving on, again, looking at inverter selection. So this is a screenshot or a section from the inverter data sheet. So max input voltage is 1,100 volts. Maximum current per MPPT is 26 amps. Maximum short circuit is 40 amps. So those three are determining factors on the input side when choosing your PV modules as well. And then when you look at your output voltages, please be mindful of the output voltage. Is it three phase, single phase, 400 volt, 11 kV, or whatever it might be? In our region, please reach out to us so that we can send you the correct data sheets. Something important to consider as well when looking at a data sheet like this, if we're talking about South Africa or Huawei in our region, it's Middle East and Africa. So typically the data sheet is written for the Middle East conditions. So your temperature conditions is a lot higher. They're working at 40 or 45 degrees. So for instance, 100 kTL in South Africa is actually capable of producing 110 kilowatts. If you look at a temperature derating curve, it's at 110 kilowatt all the way up to about 55 degrees. And only after 35 degrees does it derate to a lesser, where it's not 100 kilowatt, or it's not 110 kilowatt anymore, but only 100 kilowatt. So when doing comparisons between inverters, please be mindful of the temperature derating, and then also please be mindful of what power factor they're using when they're indicating the values. So now, if we continue with equipment selection, we're looking at panel and inverter compatibility. So on the left is a screenshot of a 100 kTL M1 data sheet. On the right, we've got a Jinko Tiger Pro 550 watt module. So this is now the comparison that you need to do when choosing both the inverter and the panel, or when you're choosing a panel to match your inverter. So your maximum input voltage is what we've got here in yellow. So the driving factor behind that is just the number of modules that you can have in a single string. So you would be looking at your V open circuit voltage. So open circuit voltage of a specific panel, 550 watt. If we just look at this, there's different wattages, 530, 535, 540, 545, and 550. So we would then typically be looking at these last columns. As I mentioned previously, we use STC ratings for design. So your input voltage maximum 1,100 volt, you will divide 1,100 divide by the open circuit voltage of 49.62, and that would indicate your maximum modules that you can have in a string. But that's also, we still need to factor in your temperature coefficient. Second thing that you need to look at compatibility is your maximum current per MPPT. So on this inverter, we've got 26 amps. So if we look at the maximum power current, IM peak, if we look at the 550, it's about 13.45. So if you times that by 2, you're just above 26, you're at a 26.9, but the inverter would then be capable of still handling it, since its short circuit current can go all the way up to 40 amps. So again, if we talk about short circuit current, if we look specifically to the short circuit current is only 14.03 on this 550 watt module. Times it by 2, as you've got 2 inputs on the Huawei for the MPPT, that would give us a short circuit current of 28 amps, which is well below the rating of 40 amps. Then the second one, or the third one highlighted here in green, is the operating voltage range for the MPPT. So that's just at what voltage does it switch off, and at what voltage does it switch, at what voltage does it switch on for operating, converting DC to AC, and at what voltage does it switch off, or it's not as efficient anymore, and that's 1,000 volts. So if you look at your solar capacity factor in your early mornings at your lower voltages, the lesser this value of the MPPT means the earlier the inverter will switch on, And the greater this value of the MPPT, it means the later it will switch off. So that's your voltage range on the MPPT. But again, when we look now at the string design or the number of modules per strings, we'll go into more detail on this one. Then nominal input voltage. So if we're looking at South Africa, our input voltage on the AC side, 400 volt. So that's just what we can withstand. Grid-tied inverters, you have to connect it on the AC side. So that is your limiting factor. Excuse me, just want to take a sip of water. Okay, so we've already done the selection now on the inverters, the panels, and the mounting structure. So the fourth component that we need is the communication device, and that is how do we access the information on the inverter? Do we access it remotely via a cell phone or a laptop? And then how does the inverter communicate or relay the information to the web? So you've got two options. You've got a smart dongle option, which is on 4G or on Wi-Fi. And then you've got a third option of the Smart Logger 3000A. So which communication device do you use? So the recommendation is to use the Wi-Fi smart dongle if you have less than 11 inverters and at least one is 40 kTL or below. So that's when you use the Wi-Fi smart dongle. The 4G dongle is in remote places where you do not have Wi-Fi available, and the 4G dongle is compatible with the inverter range from 3 kTL all the way to 100 kTL. Now, the Smart Logger 3000A, when do you use the logger? You use the logger if you have more than 10 inverters and if you have no inverter 40 kTL or below. So the Smart Logger is compatible with the 50, the 60, and the 100 kTL. So that's the compatibility of the Smart Logger. If you've got a 50, 60, or 100, you have to use the Smart Logger as communication device, or alternatively, you use the Smart Dongle 4G, but then your limitation is that you have to have less than 10 inverters. So that's your communication options. The Smart Logger is then obviously, it's a more expensive component, but it does provide you with more communication options. So it's got RS485, 3 inputs up to 80 inverters. Weather station can also be connected to it. So a lot more options on the Smart Logger 3000A. Then next component in our equipment selection is the power meter. So Huawei has got its own smart power sensor, and then there's also third-party sensors available that's compatible with the Huawei. In South Africa, we prefer to use the Unitsa range, the Unitsa UMG 604, 103, and 104. Just a quick note, Unitsa 103 is not available for the rest of the year. The manufacturer, Unitsa, has got problems in sourcing components, electrical components, and that's just a global supply chain issue. So Unitsa is only the 604 and the 104 that's currently available. But then how do you choose which power sensor to use? So you can use the Huawei Smart Power Sensor if your total AC requirement is less than 170 kilowatt and your grid incomer cable is smaller than 24 millimeter. The reason for this limitation is that the Huawei power sensor comes with its own set of CTs, and that's the limitation on the opening of the CTs. And then when you use the third-party power meter, use it when your total AC requirement is greater than 170 kilowatt and your grid incomer cables is larger than 24 millimeter. Just a note on this one where it's referring to less than 170 kilowatt and more than 170 kilowatt. It is specifically your total AC requirement. So it's not the AC requirement of your inverters, saying that you've got a factory with a total AC requirement of 500 kilowatt, but you're only putting 100 kilowatt inverter. So because your total AC requirement of the complete factory or the complete installation is more than 500 kilowatt, you will then have to use a third-party power meter. So please be mindful, it's not your AC rating of the inverters, but the total AC requirement of your installation. Okay, moving over to section number 3 is actual string design. So on a string design, we've got panels and strings. So how many panels do you have? How many strings do you use? How many panels do you put per string? And then your string and MPPT arrangement. How do you differentiate between all of these and how many do you use? So the first one is a mathematical calculation. It's the modules per string. So according to IEC standards, the number of PV modules connected in series is calculated using the formula shown below. So the first one is your minimum panel. So it says that your panels should be more than or equal to, and then it's the first component of this equation. It's your V startup. That's the startup voltage of your MPPT divided by the VOC. So that's your open circuit voltage. So that's, please be mindful, you need to compare it with the data sheets to get the correct information. Then you times it by 1 plus T minus 25, where T is the minimum temperature of PV modules at annual historical lowest ambient temperature. So this temperature rating is specific to your region or your area of installation. And then you times that with your KV, which is the open circuit voltage temperature coefficient of PV modules. So that's also a value that you get straight from the data sheet of your PV manufacturer. Then continuing on, it says that, so the first one, it says that your string should be more than or equal to, so this is your minimum number of modules. And then the second part of the formula is your maximum amount of modules. So your modules should be less than or equal to this amount here. VDC max, that's your maximum MPPT voltage range. Again, V open circuit refers to your module open circuit voltage. The T dash is the maximum temperature of PV modules at the annual historical highest. And then KV, again, is the open circuit voltage temperature coefficient. So if we take it as an example here on the bottom, on the right-hand side, we have a screenshot of a typical data sheet for our system. Open circuit voltage 48.67, minimum temperature is 16, temperature coefficient is minus 0.29 percentage per degree Celsius. Startup voltage of the MPPT is 200 volts and the maximum temperature is 40. So if you replace these values into the formulas that we just discussed, you would see that the minimum panels in this scenario would be 6 and the maximum panels would be 19. So this is a mathematical calculation. So you do get some Excel spreadsheets that can do this calculation for you, or if you're using computer-aided simulation software like Helioscope or PVSys, it would do this calculation automatically for you. But if you do not use computer-aided designs and you do your design by yourself, you would be doing this calculation by hand, and then you would get your minimum and maximum modules. So talking specifically about Excel spreadsheet, so we've got Jubaili Bros string sizing tool. So please reach out to us. We will share this Excel spreadsheet with you. It's a very easy spreadsheet to use. On the first section, you would choose the inverter, if it's 100 or 200 kTL. Once you've done the selection on inverter, it would show you the number of MPPTs and the number of string inputs that you can connect. And then also with its MPPT voltage, minimum, maximum. So the first one is your inverter selection. Second one, you would input your annual high and lows. So this is now, again, it's specific to your region. So please do not just go with a copy and paste solution or a one solution fits all. In South Africa, we do have very diverse climate conditions. So if you're looking at coastal conditions, your maximum temperature might only be 30 degrees with a minimum of 12. But if you look at inland conditions or maybe conditions close to the Lesotho Mountains, your maximum temperature can be as high as 36 or 40 with minimum temperatures going below zero. So it's very important to input this temperature condition specific to the region where you're doing your installation. Then your third input is your panel values. So you would then choose your PV module if you've got existing PV stock or you're planning to procure PV. Just make use of the data sheet, insert the values for VM peak, temperature coefficient, open circuit voltage, your NOCT ratings, and your maximum DC voltage on the panels. So once you've done these first 1, 2, and 3 inputs, then step number 4 would give you your string results. So it would tell you that on your string, your minimum modules should be 13, your maximum modules should be 28, and then for optimum, it should be 26 plus minus 1. So number 4 is all dependent on the information that you've inserted here in this first 3 steps. Then continuing on, so string sizing example. So we're actually running through physical examples now. So when we started this presentation, we said we look at AC requirement. So in this case, we've chosen 60 kilowatt as the AC requirement. Step 1, DC to AC ratio. So we've decided to use 1.3 times the DC. So that would mean the DC is 78 kilowatt DC. Your second step would be to check your space constraints to see, do you have enough space to install 78 kilowatts of DC. In this scenario, we selected it to be okay. Step 3 was we select the inverter. The inverter was a 60 kTL or 60 kilowatt. Step 4, we select the panel and confirm compatibility. In this scenario, a Jinko Tiger Pro 450 watt was used. So to calculate the number of modules, we take the total DC requirement, 78 kilowatt, divided by the 450, which is our panel. That means that the number of panels to achieve this DC to AC ratio would be 173 and a third. So this is just now your first step or your initial one. So if we now go on to the next step, let me just see, so excuse me. So the next step is to actually use the string designer and see, listen, how many strings is actually recommended. So on this one, so in this case, they've chosen 171 pieces of 450. That would be a DC 76.95, a ratio of 1.28. 60 kTL has got 6 MPPTs with 12 string inputs. So that means you've got 2 inputs per MPPT. And then the inverter itself has got 2 DC disconnect switches. So using the string sizing Excel sheet, that's the Jubaili Bros one. And if we inserted all the module details, it gave us a minimum of 6 modules per string, a maximum of 21 modules per string, with the optimum being 20 plus minus 1. So in the previous slide, if we used a DC to AC ratio of 1.3, it calculated it to be 173 and a third of a panel, but then obviously we can't do a third. But the optimum range, according to the string size, is 20 plus minus 1. So in this one, it was recommended to use 19 panels per string with 9 strings total. So the 60 kTL has got 6 MPPTs with 12 strings. So that means you're all fine. You've used 9 of the possible 12 inputs, meaning you still have 3 spare. But then using 19 PV modules per string, 9 strings. Example number 2, we're running through the same steps, 195 kilowatt AC requirement. So in this instance, they've chosen 100 kTL, 2 pieces. That would give us 200 kilowatt. But in DC to AC is 195 times 1.3, 253. In this instance, they've chosen a Jinko 535. Again, doing your calculations on the panels, that would mean 485.9 panels, which is rounded off 486. 486 pieces of 535 gives you a DC of 260 kilowatt, ratio 1.3. But in this scenario, again, using that string sizing Excel spreadsheet, you would have chosen your inverter, input your panel data, and based on that, either using the string sizing Excel sheet, or if you did a manual calculation, the minimum panels would have been 6 and the maximum 21, and the optimum range was 17 plus minus 1. So in this instance, it was recommended to use 18 panels. So 486 panels divided by 18 panels per string means that you're going to use 27 strings. So specific to the 100 kTL, 100 kTL has got 20 inputs. So for the 2 of them, you've got 40 inputs. You're only using 27 out of the 40 inputs. So again, you're all good and you can continue using that. So continuing now is when we're talking about MPPT arrangement. So example 1, example 2, that's the 2 inputs that we've already did our calculations on. So it says 9 strings with 19 panels per string. So we're using 9 out of 12, and in this one we're using 27 out of the 40 strings. So if your design does not fill all these inputs, you should spread the strings evenly between MPPTs and between DC disconnect switches, and then maximize the number of MPPTs used. So if we look in this first scenario, we've got 6 MPPTs with 12 inputs. We were using 9 strings, so that would mean your first 6 strings would be 1 string per MPPT, and then the remaining 3 strings, you would then have 2 strings on the first 2 inputs, and the third string maybe on the last input, just so that you can split it between the 1 and the 2 DC inputs. So that's how you would do it on the 60 kTL. Then in example 2, we've got 27 strings out of the total 40. So you've got 200 kTLs. So If you want to, you could divide it. So you could have 13 strings on the one and 14 strings on the other one. So again, what you would do is you would first populate one string on each one of the MPPTs. So if you're looking at a 13, so that would mean all 10 MPPTs, so it's got one, you're remaining with 3, and then you can just split it 1, 2, 3 between the 3 different DC switches. Then on the second inverter, where you had 14 strings, again, populate the first 10 inputs of the MPPT, and the remaining 4 split it maybe 2, 1, 1, just so that you're dividing all of the strings among the DC switches. So that's how you go about doing the MPPT arrangement. In this next slide, this is an image from the user manual of the 100 kTL. So all Huawei inverters has got a recommendation of how to arrange your strings. So with the 100 kTL, you've got 20 strings available. So how do you go about it? If you've only got one string that you want to connect, you can connect it on any one. If you've got 2 strings, they would recommend using PV input 2 and 10. Then using this graph, you can continue and see which slot Huawei recommends you using on your strings. For instance, if you've got 9 PV strings, they recommend using PV input 2, 4, 6, 8, 10, 14, 16, 18, and 20. So this is a recommendation from Huawei on how you should be balancing your strings across the inverter DC inputs. Then also looking at your MPPT arrangement. So we've got one MPPT with 2 inputs. So the 2 strings that you connect to a single MPPT should be of similar location and configuration. So if you look at a housing scenario, MPPT 1 should have string 1, 2 on one section of the house. You should not be mixing and matching different strings. So if you've got something perhaps on the south side of the house, don't mix it with a string on the west side. Or if you've got north, don't mix it with the south. So typically keep your north, your south, south, your east, east, your west, west. So just try to have them in similar conditions. So also try and have a look also at shading factors that can impact your strings, so that you connect strings. If there's perhaps one string that might have a little bit of shade, try and keep that string separate so that it doesn't influence the whole MPPT, or it doesn't have a big influence on any of your other strings. Continuing with MPPT arrangement, a reasonable layout of panels arrangement to reduce the impact of block degeneration. For string inverters, when a string is blocked, other unblocked strings generate normal power, so the string managed arrangement should be to minimize the span of the height. So if you look at this typical installation cases, you've got a landscape scenario with shading on this bottom section. So try and use your first string on the 2 top panels or the 2 top rows, and then your second string on the 2 bottom rows. That means that only the second string might be influenced a little bit by these modules. But then also it's actually recommended to use your panels in a landscape orientation due to the diodes. So typically a panel has got 3 diodes built into it, split evenly. But then also nowadays we also have half cell modules where it's one module, but it's almost split into 2, so you have 2 different sections. Then the second installation here is portrait installation. Again, you can have top row on one string, middle row on one string, and your bottom row on one string. So do not mix in a portrait scenario the top with the bottom, or mid and the top. So try and keep it as even as possible. This third scenario is just two rows or 2 rows of portrait installation. So you can just have that on a single string. But then again, if you look at your different scenarios on MPPT 1, no shading, 2 no shading, 3 shading, then on 4 there's limited shading. So it means that only MPPT 4 will be limited by the shading. Then running a simulation. So there's various simulation software available that you can use. I think the most popular would be PVSys and Helioscope. But then there's also some more simulation software available, like Homer, if you want to go more into battery energy storage simulations. So PVSys, if we're just in this example, we're looking at PVSys specifically, but it's more or less the same between the different simulation software. So PVSys is a solar system design tool that represents results in the form of a full report, specific graphs and tables and data that can be exported for use in other software. Key features: system sizing, shading scene, simulation results, grid storage, meteor norm, components, and aging. Then continuing importing the pan OND or .bat files. So OND or BAT files, you can get that specific for the inverter that you would like to use. If it's not preloaded on the software, you can just send us an email. We will send you the OND file that's got all of the information on it to use within the program. Okay, this is just showing you continuously how to import the data. Again, if you do need any of these files, please reach out to us. We will then forward it on to you to use in your simulation software. So creating a 3D shading scene. So in PVSys, this would be a typical rooftop installation. This would be the roof area available for installation. You would then also arrange your modules. And then in this one here, you can see this pillar is a possible point of shade. It can put shading on a module. So if you input all of these 3D characteristics into the software, it will then run a simulation to show how much shading this pillar can affect on your system. And then it will then give you your annual yield or your annual results. These results are typically available in graph form, but again, it's very similar in Helioscope or PVSys or any software that you're using. So on the software as well, you can have financial parameters. So you can input your capital expenditure on your cost of the system. You can input at what time of life you would be looking at replacing components. So you could do a simulation where you say that after 7 years, I would be, budgeting to replace all of my inverters with a cost attached to it. That will then give you financial results to say that, listen, your payback period is 3.6 years, but then you're planning on doing some maintenance, or you're doing replacing of components after year 5, 6, or 7. So that would be expenditure of capital again. And then you would have a payback period again, where if, for instance, your capital expenditure has put you back into the negative, it would take you again 1 year or maybe half a year just before you've got ROI again. So that's just financial parameters that's available in these simulation software. So economic analysis, again, that's looking at financials. This system now is specifically to a 10 kilowatt peak solar system. Below are the financial outputs based on Jubaili Bros commercial proposal. So this quotation would be the total quote or the total cost of the system. This output would be based on the simulation of the software, saying this is how many units you would get per year, 17,200. Yearly energy saving would be AED 6,380. Total savings over 20 years, payback period between 5.84 years. So this is just all the financial or economic analysis that's available in it. In this graph, it's just a physical or demonstration of how your finances would be impacted. So first of all, you're in the negative of your capital expenditure to install the system, but then you've got your system, or as the time continues, the system has saved you until it reaches that 5.84 years. After that, you're into the green section of just saving. Right. So that's it for today's presentation. I think a lot of it is really useful if you're using computer-aided simulation software, where it's assisting you with the string sizing and design. But then also we do have offline options available with the Huawei string sizing tool. Or then if you want to go back to the old school way of calculating everything by hand, you know now how to use this formula. So just a quick point of to mention is that the slides will be shared with all of you. It will be sent automatically to the email address that you used to register. Okay, so let's quickly have a look at the question and answers. So first question, let me just quickly see if it's published. Any specific recommendation, please, for stringing in floating PV system? Floating PV system, your design parameters is again, you're still limited by the open circuit voltage on the module. You're still limited by the same characteristics of the inverter. The only change between a floating system and a system on land might be your temperatures. Recommendation would still be to use the closest point on land as a maximum and minimum temperature point. So you would still be using the minimum maximum temperatures of that region on your design tool. So if you're looking at a system where it's floating on land, well, it's floating on water, not too close to land, maybe you can deduct 1 or 2 degrees on a maximum temperature, but then also on a minimum temperature, you would not really deduct. You would actually keep it as the same, or maybe add 1 degrees, as typically water is a good conductor or storage of heat. So for floating PV, I would say your basis of design should still be very similar to as if it was on dry land. You can maybe, if you want, just play around with the temperatures by 1 or 2 degrees, but not more than that. And typically, that's not going to change your actual values by more than one panel. That's from what I would say. The next one, on maximum of 20 inputs. Does that mean I can do a maximum of 20 strings? Yes. So if we look at a 100 kTL inverter, it's got 10 MPPTs with 20 inputs. So that means you can have 20 strings connected to it, but then your limiting factor again on the strings, remember, your string should still be within the voltage range. So you can't have more modules per string. And then the limiting factor is your short circuit current or your operating current. So if we look at an example like I had in my one scenario, if we're looking at a Canadian 550 watt panel, which had a short circuit current rating of 14, the Huawei has got a rating of 40 amps. So you're well within that range, but then the operating range was 13 amps. So the 13 times 2 was 26 amps. So as long as you're within the current ratings, you can use all the inputs available on the MPPT or on the inverter. So yes, if you're just looking at 20 inputs, 20 strings, that is correct. But please just bear in mind your short circuit current ratings and then also your number of modules per string, just to make sure that you do not exceed any voltage or current ratings. Does the design tool work with third-party systems? So the Jubaili Bros Huawei tool is specific to Huawei inverters. So if you look at your selection criteria, only the Huawei inverters is available. I'm sure that if you want to do the effort, you can actually modify or build up your own Excel spreadsheet if you want to use any other third-party inverters like SMA, SunGrow, or whatever it might be. But the tool specific from us, from Jubaili, is specific to Huawei inverters, as we are loyal to the Huawei brand and we are a VAP and certified solution provider for Huawei. So our tool is Huawei only, but then you can build up your own. Next question from Lawrence. While oversizing the system, do you still need to take losses into consideration? So yes. So if you've on a typical DC to AC ratio, you do not take the losses into consideration. Then you would just say 100 kilowatt, I'm going to use 130 kilowatt DC. But if you do take losses into consideration, if you know, or from a simulation, you know what is your AC losses or your DC losses, or you know that you've got, if your losses is known, then you can take it into consideration. But if you have not exactly quantified your losses and you do not know exactly what they are, then you do not take it into consideration. You work on an assumption basis. So that question is very, very limited to what you know of the system or of the installation. What's the difference between rated output of the inverter in watts and VA? Okay, so the rated output of the inverter in watts and VA. So VA does not take power factor into consideration. So if it's 110 kVA, it means the power factor is constant or perfect at 1. The wattage does take power factor into consideration. So typical power factors is between 0.8 leading and 0.8 lagging. So watts and VA, that's your power factor. So your power factor is dependent on your installation or your factory or how it is. But typically real world scenarios between 0.8 leading and 0.8 lagging. So typically you're looking at watts and not at VA. The VA is rated at a perfect power factor of 1. Then next question from Kashif Nadim. My question is net metering related. Can I? So net metering is dependent on your country or if you're specific to a certain region, and it depends on what's the bylaws in that region. So if you're using the smart power sensor, either from Huawei or a third party, you can block the metering or you can block export. But if your local government allows it, then typically, like in South Africa, you need to register with the local municipality and NERSA, depending on the size of your system. And then if that government or your local municipality has got a smart meter that can actually read in both ways, then you are allowed net metering. But net metering that is specific to each country, specific to a certain region in a country, as laws might differ between different regions. So your question on that one would be region specific and what's the bylaws for that specific region. Any dealer in Kenya? So yes, Jubaili Bros has got representation in Kenya. So please, again, feel free to reach out to us. You can send me a mail and I can forward it on to one of my colleagues in Kenya. So we do have representation in Kenya. So please reach out to us and we can assist you in any possible way. Can the simulation tool generate the bill of material automatically? So in a limited way, yes. If I'm thinking about helioscope, for instance, the bill of material that it would generate would be estimates. It would work on estimates between the ranges of where your inverters is installed in the field, where your AC tying point is. So that's typically on the design, you would see indication in meters. But then typically it will only give you your electrical things. So it would give you a bill of material for the inverter. It would give you a bill of material to say your number of panels and which panels. So it would give you total inverters, total panels. It would give you an estimate on your AC cables. So if you specified in your design, I'm using 25 millimeter cables, based on your design and where the inverters are installed and where your tying point is, it would give you an estimate in meters on how many meters on AC cable you need. And then also on DC cable, where your panels is installed to where your inverters are installed. It would give you an estimate on the DC cable. But then if you're going to finer details, if you're going to the amount of trunking that might be required or wireways and stuff like that, that won't be part of the bill of materials. So generally, simulation software only give you a brief or a very limited bill of materials related to the electrical side of what data you used on the input side. Next question. Can you also organize for us training solar PV systems with storage devices? So yes, Huawei do have some training material available on the residential side for storage. We are working on the commercial and industrial size storage solutions. So very soon we will be having commercial and industrial storage PV design or training. So just be on the lookout, follow us on LinkedIn, and then just have a look out when we're going to have training specific to that. Okay, then I have a project I need to tender for. Can you assist with the design and costing? It's in Nigeria. I would also like to have the simulation tool. What capacity? Okay, so this is a response to a question inside the chat. If I look at the initial one where it says I have a project I need to tender for, can you assist with the design and costing? It's in Nigeria. Yes, we will be able to assist with design and costing. Please reach out to us, send us all the details involved. If you've got the tender documents, we will gladly assist you on the designing side and specification side on the Huawei inverters. But when it comes to the installation costing, you would do installation costing by yourself. But when it comes to the PV system design, we will definitely assist on design and costing. So please just send us the information and we will assist you. Next one from Sekitoloke. Do you also have a sizing tool? We can also use solar system with storage devices. So we do not have an offline, we don't have an offline tool that you can use. Huawei has got its own design platform that's very limited on the residential side. So Huawei has got its own smart design, so we can share the link for you. Then you can also use that. But when you're looking at the larger CNI storage, we don't have a system sizing tool or a design tool. That's generally spec'd by the engineers. So if you've got information, share it with us and then we'll see how we can best assist you to get a full solution for you. Okay, next one. I think that's a response on that initial one where he was looking for the assistance on design and costing. So the system size is 1.3 megawatt. And then, I'm solar sales engineer, JB Solar, Nigeria. Okay, so Sidipo, thank you very much for sharing your information. So that's one of my colleagues in Nigeria. So please please reach out to him, share all the information, and then he will gladly assist you. Next one, if you surpass the short circuit current, does it affect the inverter in any ways? Yes. So if you surpass the short circuit current, it does. The inverter can withstand the short circuit current for a very small limited time period. So it's between 0.1 and 3 seconds, depending on the severity of the short circuit current that you're passing it by. But yes, if you do surpass the short circuit current, it can damage the MPPT of that inverter. Right, so that's it. That's all the questions that we've got for now. I just quickly want to double check in the chat to see if there was any questions there that was perhaps raised that I could have missed. Okay, just want to mention again, slides will be shared automatically after this event. It will be sent through email that you use to register for the event.